Now, moving on to loaded spring systems in simple harmonic motion. So, for simple harmonic motion, we need to make two assumptions. Firstly, we say that the mass of the spring is negligible. And secondly, we say कि जो हमारा spring है, it obeys the Hooke's law, which means that the elastic limit of the spring is not being crossed. और हमारी third assumption ये है कि the amplitude of vibrations must be lesser than the equilibrium extension. So now, if we consider a vertical massless spring, जिसके ऊपर m kg का load लगा हुआ है, and it is bringing about an extension of E. So when we pull the the mass by a displacement x to bring about oscillations in the spring, जो हमारी new total extension होगी, it will be calculated as E plus x, where E is the extension of the spring and x is the displacement. और जो forces act की हैं on the spring, they can be solved into the vertical direction to derive the relationship between time period and the mass or between time period and extension. So as you can see in the diagram, जब system equilibrium में है, the vertical forces are balanced and hence we can say the weight is equals to Ke. And you can see this in figure B on the left. In the next figure, figure C, you can see that the resultant है of the vertical forces, it basically causes the acceleration of the mass. So as we know, F is equals to ma. So if we substitute the values of F, which are the forces acting on the spring, we get mg minus k multiplied by E plus x is equals to ma. And now if we substitute the equation in part 1 in the equation in part 2, we get A is equals to minus kx over m. So हमने पीछे कैलकुलेट किया था कि if the system is in simple harmonic motion, उसकी acceleration will be equal to minus w square x. And now if we substitute the values of a over x from the equation above, we get w is equals to under root k over m. So now since mg is equals to ke and our angular displacement is equals to 2 pi over t, अगर हमने period of the system निकालना है तो we'll get the equation 2 pi is equals to under root e divided by g.